So this is a video about Euler's formula and its applications. And in this video, I will talk about three um, topics. So first, I will give you the definition for the Euler's formula and some elementary computation. How do we compute Euler's formula? And then for the second topic, I will talk about some properties for the Euler's formula, and of course, those properties are important because we may use those properties to compute the Euler's formula. And for the last topic, I will talk about some applications. Why do we have to learn Euler's formula, and how can we apply Euler's formula to other problems? So that's the purpose for this video. So let me just begin with the definition. So what is Euler's formula? Okay, so the just Euler's formula. Okay, counts the positive integers up to n that are relatively prime to n. Okay, so in other words, so if we denote En to be the Euler's formula, then we have this. Okay, so so if you have my notes, actually I use another symbol for the Euler's formula, but because I'm using a Word file in typing the words here, so that's why I use another notation. So I used capital letter E to denote the function. So this En now is nothing but just the number of integers k, okay, such that 1 is less than or equal to k, and k is less than or equal to n, and also GCD of n and k has to be equal to 1. So we just count the number of integers, number of positive integers that is between 1 and n, and then and that integer is relatively prime to n. Okay, so that is a function. That means Euler's formula En, okay, is a function on positive integer n. So for example, how do we compute E9? Well, we just count the number of integers which is between 1 and 9, and that integer is relatively prime to 9. So if you directly count the number, well, you can get this Euler's formula for 9 is equal to 6. And the reason is since 1, 2, 4, 5, 7, 4, 5, 7, and 8, those integers are relatively prime to 9. So you just have to get all the integers which are relatively prime to 9 and is less than or equal to 9, but is bigger than or equal to 1. So here we have 6 many, namely 1, 2, 4, 5, 7, and 8. So those 6 integers are all relatively prime to 9 and is between 1 and 9. So that's why E9 is equal to 6. So that is how we get the value. Well, of course, if the number n is more like this case n equal to 9, you can I mean, you can write down all those integers relatively prime to 9, but it's between 1 and 9. Okay, you can do that. I mean, you can just write them all out and then count the number. But on the other hand, if the number is very big, okay, so this is a remark. Okay, if n is small, we can still get en by direct counting. Okay, that's fine, you can do that. But however, okay, however, if n is very big, say 1000, okay, then it is not easy to compute or to get en just by counting. Okay, it's almost impossible, I would say. Okay, because it's just too many. Okay, because you have to count all those integers which is between 1 and that number n, for example 1000, 1 to 1000, those numbers which are relatively prime to 1000, actually there are quite a lot. So that's why we need to find some other better methods to compute en. Okay, so we just have to develop some other method rather than always referring to the definition. So we have the basic definition about Euler's formula. So you may ask, okay, why do we have to learn this function, the Euler's function or Euler's formula? Why do we have to count those numbers relative prime to n? What's the reason? What's the point of doing it? Okay, so actually, I can give you the reason. Okay, so if you have my notes, so well, I think I have to click it. So this is the lecture notes. So you should also get the notes on Moodle. Okay, so actually, if you look at my notes, okay, you can see the basic history behind that Euler's formula. Okay, you can see that in the very first paragraph. Okay, in fact, the reason why we call that Euler's formula is because it was invented by a mathematician called Euler. Okay, so it's almost like 300 years ago, and actually it's not something new, of course, and you can see the background. Wow, actually, this function, it has some other application. Okay, not just for counting integers relative prime to some other positive integer, and in fact we can use it, okay, in a very tricky way, you can say, actually. And it's also very useful when we are solving some problem about congruence. Okay, we learned that congruence relation in the last videos, and in fact this Euler's function has a very good application on congruence. Okay, so we will see that. Okay, so you can look it up from the notes, and also of course you can see those details on the notes as well. So when you're watching this video, I suggest you to have the notes and those related material available on your computer. Okay, then when you are listening to this video, then you can just read the notes and then see if you have any question in understanding the material. Okay, let me just go back. How can I go back? Okay, so here. Okay. Anyway, so we just have the definition. So we still have a lot of things to do, as I said, because in the very elementary computation, or just by direct counting, it's not a very good way to get the value for the Euler's formula. Okay. Now before we go further, I mean before we can get some other methods, so we have to I mean, I have to give you some basic facts. Okay, so facts. Okay, for the Euler's formula. Now, for example, if you compute En, okay, then of course this will give you 1, okay, because uh, it's very by the definition, okay, that is easy, okay. So that, because the only number which is between 1 and 1 and is relatively prime to 1, of course, is 1. So there's only one possibility. Okay, so we have this, and we also have this. Okay. Now, for example, if you have a prime number p, okay. Now, prime number, okay, prime number is a very special case, in fact, and that is very important in our computation as well, because prime number can um, save us a lot of time, because it has some very simple properties. So, for example, if now p is prime, then how can we get the Euler's formula for p? Well, in fact, that is p minus 1. Okay, so why? Because now the reason is very easy. Okay, because okay, let me just type it. Okay, so for p being a prime number, a prime number, and the reason is the following: because you just count the number. So actually, because there are exactly p minus 1 many integers. Okay, you just write them all out, actually, because in this case you can see that actually you have okay, so k is less than or equal to, I mean, k is bigger than or equal to 1 but less than or equal to p. Okay, and also GCD of p and k actually equal to 1, because why? Because those integers, you can write them all out. It's just 1, 2, 3, 4, okay, dot up to p minus 1. Actually, any integers between 1 and p minus 1 except p. Okay, I mean, so you just, if you have to consider all integers between 1 and p, in fact, the first p minus 1 many integers, they all relatively prime to p. You can easily see that, because p is a prime number. Okay, so there's only two divisors for p, namely 1 and p. So in other words, all the numbers which is strictly less than p will not be a divisor, as well as they don't have any common divisor to p. So that's why they're all relatively prime to p. And so we have this special case. If p is prime, then the Euler formula for p is just p minus 1. So it's very easy. Now, but don't just think they're very easy, but in fact we will use those facts, okay, to build up some other formulas. Okay, so that is the purpose why we have to talk about those properties. Okay. Now, after these two facts, let me give you some other properties. So actually, I'm I'm talking about the second part already. So let me give you two important. Oh, sorry, so I pressed it wrong. Two important properties. Okay. So number one. Okay. So number one is if GCD of M and keep going back. Okay. If GCD of M and N, okay, is equal to 1, then in fact the Euler formula of the product of M and N is just the product of the Euler's formula. So in other words, you can distribute this Euler function among those products, okay, as long as M and N, they're relatively prime. Okay, that is the first property. Okay, and the second one is this: e p to the power k, in fact, is equal to p to the power k minus p to the power k minus 1. So we have seen one special case already. So that is when k equal to 1. If k equal to 1, then e of p, that is exactly equal to p minus 1, because p to the power k minus 1 is just p to the power 0. Okay? Oh, I have to write down if p is a prime number. Okay, that is important. That's a very important assumption. So that is very useful. Okay, actually these two properties are very useful. Now number one property, I won't prove it. Okay, because the proof is a little bit long, and I don't think that is very important to us, and it may not be that necessary to our case. So you can just take the first property as a fact. Okay, just use it. If you have two numbers relatively prime, then the Euler formula for the product is simply the product of the Euler's formula. Okay, so you can use it. But on the other hand, the second one, I will prove it. Okay, I will show you the proof. In fact, the proof is already available on the notes. So let me go through it with you. Okay, so I don't want to type it, but let me just go straight to the proof. Now, actually, the proof is quite easy. Okay, so again, in fact, we can apply the very basic definition to this problem, because even though we have p to some power k, that number may be large, but because it's special, it's a power of prime number, so it's a special case, because not many integers is in the form of one prime number powers. Okay, so it's a special case. So that's why we can compute it by counting, sort of like counting. Okay, so let's see how we can do that. Now, for example, we just consider any integers m, okay, between 1 and p to the power k, okay, because p now is a prime number. Now then, if the GCD, I should say, okay, not equal to 1, but you consider the GCD of p to the power k and m, okay, then because p is prime, okay, and in particular, okay, when you're considering the GCD, you have to consider the divisor for p to the power k. In particular, what are the divisors for p to the power k? Well, you don't have many choices, but just 1, p squared up to p to the power k. So there are not many cases. So actually, how many? Well, it's like k many. Okay. Anyway, so there are just that possibilities, and the only way for the GCD not equal to 1 is what? Is when this number m is a multiple of p. If m is a multiple of p, then of course you have GCD will be some power of p. Okay, so in other words, okay, if this integer m is not multiple of p, then the GCD will be equal to 1. Okay, right? So we have this, and then okay, so maybe I have to go to another page. Now we look at this page. Okay. Now we look at this. Now the multiples of p that are less than or equal to p to the power k, actually, what are those multiples? Okay. Well, actually, you can keep writing the multiple where we can multiply 1 to p. Okay, you multiply 2 to p, or you can multiply 3 to p. Okay, and then up to what integer? So you can take the multiple to be p to the power k minus 1. Now, but if you multiply these two numbers together, you get exactly p to the power k. Okay, so if you count those multiples, how many of those multiples? So actually, you have p to the power k minus 1. Okay, so those are the multiples. In other words, now, if you want to count those numbers which are relative prime to p to the power k, then you have to subtract those numbers which are not relatively prime to p to the power k, right? So, but how many of those numbers? Well, as I said, because all those numbers are multiples of p, so they're up exactly p to the power k minus 1. In other words, the difference will always give you those numbers relatively prime to p to the power k, and therefore the Euler function of p to the power k is just p to the power k minus p to the power k minus 1. So it's a way of counting. Okay, it's not that easy, I would say, but if you think about it in a step-by-step way, it's not that difficult to see that, well, you must have that relation. Okay, so but that is a very special case when your number is a power of p. If it's not, then you have to apply another thing. Okay, but in fact, if you of course, the second property is just what I just it's exactly what I told you, but as I said, not many integers are in the form of p to the power k. So what can we do? Well, in fact, we can combine this first property and the second property, and then we can use these two properties together. Okay, and then try to compute the Euler function of some other integer. Okay, so I will continue in the second part of the video.